Welcome back. Let's talk about Chapter 4. Chapter 4 is all about techniques. It's a really important chapter. It's so important we're going to spend twice as long on it. Okay, and we're going to work lots of extra problems. So what I have here is the notes that are posted, and I'm going to point and talk. So you might want to print these out and follow along, or whatever works for you. But the first concept in this chapter is something called node voltage method. So what you're doing here is you're using KCL, you're using Kirchhoff's current law. That is, you're summing currents at a node, but the terms you're using are V over R terms and I terms. All right? And the convention is in is negative and out is positive. So by Ohm's law, I equals V over R. So here's a little circuit right here. I've got a 6 amp current source, and I've got these 3 resistors in here. So what you do on these guys is you pick the bottom node as 0 volts, and that's always going to be the case for us. It's not going to get more complicated than that. So the bottom's 0 volts, and then along the top, between every element, you put a node. So if you start here at 0 volts, then there's an element here, and so above that you put this node. Let's call it V1. You could call this node 1. And there's a voltage V1 there. And then likewise you go above this resistor here, and there's a node. And then between this resistor is a node. And between these 2 nodes is a resistor. And between these 2 nodes is this resistor as well as this resistor. Right? This resistor, the 5 ohm resistor, is between nodes V2 and node 0 at the bottom. Likewise, this 15 ohm resistor is between node V2 and node 0 at the bottom. So basically there's a node between every, there's an element between every 2 nodes. Or you could say there's a node between every, no, that's the first thing I said is right. All right. So, so if you label these currents, I sub A, this current here through the 10 ohm resistor, and label this current through the 5 ohm resistor IB, and label this current through the 15 ohm resistor, label that IC. By Ohm's law, we can come up with expressions for all of these I's by using the potential difference at the nodes. Because it's a potential, that is a difference between voltages, that causes current to flow. That is, there's a potential difference that causes current to flow. So the potential between node 1 and node 2 will make this current flow. So you have to have guessed on these current directions, which you try and guess correctly. Now we'll talk more about that, but basically I'm guessing on these current directions. So I'm assuming the 6 amps is coming up here and then going this way. So that's more than a guess. That's basically agreeing with this 6 amp source. The current direction here is agreeing with the 6 amp source. But here I'm guessing, and really there's only one correct guess for this simple circuit. I mean, the current's going to come here and it's going to split. And then those currents are going to join back up at this node and go back to the source. So that's what's going to happen. So we kind of know the current directions on here. We don't have to guess too much, but sometimes we have to guess, and we'll talk more about that. Anyway, here's the way I come up with these expressions for I sub A. So once I have this I sub A direction, in this case it's going to the right, in order for that to happen, then V1 must be bigger than V2. That is, the voltage at this point must be bigger than V2. Okay, so the expression is V1 minus V2, that's the potential difference, over the resistance. So in this case, we're just using Ohm's law, but the voltage is a potential difference over the resistance. That gives us the current through this device. Okay, so that's the kind of stuff we're going to do. We're going to look at these potential differences and a little bit more about potential differences. So the nice thing about this method is it sort of models the way you do testing in a real circuit. Like if you had a voltmeter in a real circuit, it would have 2 wires. And what you would do is you would take the black wire and you connect it to ground. You'd connect it to what's being used as the ground for that device. So you'd hook it up down here. This is the ground. For these circuits, the ground's always going to be at the bottom. But then you take the other wire and you start poking around on the circuit, and you're going to get different voltage readings on the circuit as you kind of poke around. So if you had the negative terminal, you know, down here, and you measured here, you'd get some voltage. And then if you move the wire over here, you'd get another voltage, and it would be less than this voltage. Right? That is, V1 would be bigger. That is, if the current was in fact going this direction, that would be the case. Okay, so that's the expression for I sub A. It's V1 minus V2 over 10. And we can come up with this expression for IB, the current through the 5 ohm resistor. It's some voltage V2 up here and some voltage 0, well, a known voltage 0 down here. So basically V2 is pushing this IB current through. So the expression by Ohm's law is just V2 over 5 for IB rather. And IC is just V2 over 0 by the same logic. Okay, so these are our expressions using Ohm's law for the 3 currents in these devices. And the only tricky thing now is that we're using a potential difference for these currents. Okay, now that we have expressions for currents, IA, IB, and IC, we can sum them using KCL. So we have a node here, and we have a node here. We can write 2 KCL equations. So I use this notation NV1, which is saying I'm using node voltage at node 1. And so we have our convention here. Out is positive and in is negative. So we have I sub A leaving node 1. So that's positive. And we have 6 amps coming into node 1, so that's negative. So IA minus 6, they sum to 0. And then plug in your expression for I sub A. Because what we want in the end is we want V over R terms and I terms. And it may seem funny, but you tend to, for this method, you tend to keep you want these V terms really, because that's what you're going to solve for. All right, and it's just the way it works out. You'll see more later as we work more problems, but you get it to look like this. It's an expression with just V terms in it. Okay, and yeah, so did I say it? You substitute I sub A, you substitute this one in there, and you get this. All right, now we have another node. We have the second node, so we can do a node voltage equation for the second node. That is, we'll apply KCL at this second node. So currents going out are positive, currents going in are negative. So I have IB and IC going out of this node, right? They're leaving. So IB plus IC, you write. And then I've got IA coming into this node. So that's going to be negative, and those sum to 0. Then once again, take your 3 equations for IA, IB, and IC and substitute them in here. And you get, for IB, you get V2 over 5, and IC, you get V2 over 15, and IA, you get this ugly thing. So this is the form that the equations take for node voltage method. They're all expressed in terms of these voltages at different nodes. Okay, they look like that. And from then on, if you notice, we have 2 equations here, right? 2 equations and 2 unknowns, V1 and V2. So mathematicians tell us that when you have that situation, there is a solution. So that from then on, it's just a algebraic method or some method to solve these simultaneous equations. Now I'm going to use matrix method. That's what I use in my calculator from way back. And I'll show you how to do matrix method, and I'll show you how to do it in some other tools as well. But basically that's it. Now I went kind of in detail, but what we're gonna do, we're gonna typically write these equations directly, a little more directly. We're not going to take the time to write these, but I just wanted to develop it a little bit more slowly for you. Okay, we'll work many problems on this, and we're going to actually use this throughout the rest of the semester. It's very important stuff. this isn't the end of it. You haven't seen the end of this yet. Right, that's the first method for this chapter. The second method for this chapter is something called mesh current method, which is the sort of the flip side, the analog, you might say, the flip side of the previous method. So what we're doing here is we're using Kirchhoff's voltage law, or KVL, but we're using V and I over R terms, mostly I over R terms. We express the final expressions with a lot of I's. Okay, then there's something called superposition, okay, which basically means that each current has independent effects and can be summed. I'll show you what that means. So here's this very same circuit that from before, except now we're going to use KVL, and that is, we're going to use mesh current method. Very same circuit. Oh, except I have a voltage source instead of a current source, so that is different. Okay, there's a 10 ohm resistor, a 5 ohm resistor, a 15 ohm resistor. So we have our infamous Ohm's Law where we know V equals IR. So let's kind of put polarities on this, or just check that the polarities are all good. So I've got a positive terminal. That means there's going to be current coming out of this guy and going through the resistor. And so the resistor will resist that current flow with this polarity here. That current will split and go to the right and down, and these two resistors will resist that current flow with this polarity and this polarity on the positive negative signs. So you get that all set up. Then we could label these, the voltage across the 10 ohm, and we could label the voltage across the 5 ohm, and VA, VB, and VC, and we could come up with expressions for those by Ohm's law. So VA is I1. So we have these loop currents here. I1 is going around this loop, and I2 is going around this loop. So we can use that for Ohm's law. The current through this guy right here is I1. So we have 10 I1 for the voltage by Ohm's law. Likewise for VC, we have 5 I2 by Ohm's law. Okay, then the tricky thing here is the voltage expression VB. That one we have to apply superposition. So what we're saying is that the voltage in this resistor is due to two effects. It's due to the effect of I1 current, and it's due to the effect of I2 current. We have to apply superposition to those two separate effects. That's just the way the method works. We'll talk a little bit more about how to deal with that and why that is. But anyway, the voltage here is going to be the voltage due to I1, so that's 15 I1 by Ohm's law. And then because I2 is in the opposite direction of I1, you see I1 is going down through this resistor, but I2 is going up through this resistor. Then we subtract the effect. So by Ohm's law, the voltage effect due to current I2 is negative 15 I2. Okay, that's superposition, and you'll get used to it. So at that point, we can sum the voltages around each loop. So I'd like to write MC1 for mesh current 1, and we're going to sum the voltages going around here. So we're coming into the positive terminal, so that's positive VA. We're going around this loop. We're coming into the positive terminal, it's positive VB. We're coming into the negative terminal, so it's negative 20, and those sum to 0. That's KVL. Then we substitute this VA and VB expressions in here, and you get this stuff. VA is 10 I1, right? VB is these two guys. These two terms is VB. And then 20 just carries down. And so this is one equation. You can sum the loop. You could do this second loop. You can use KVL on this second loop, and you get we're coming in the positive VC terminal, so it's going to be VC. Oh, right here. Coming in positive VC, it's VC, and then you're coming in negative VB, so it's negative, and those sum to 0. Those are the only two elements in the circuit. Then once again, substitute these two equations in here, and you get this thing. So what we have is two equations that are in terms of i's now, right? There's I. There's two equations and two unknowns, I1 and I2. So once again, there's a solution that we can solve by various methods, and we'll use matrix method most of the time. So that's the methodology. One other thing, we typically, when we're writing these loops, we'll go directly to these two. That is, we're sort of doing a KVL while we're also doing kind of an Ohm's Law, a little trick. We sort of write these all in one go. Okay, that's just a good level of abstraction to be able to work at. Okay, that's the second main concept in this chapter, and we're going to spend lots of time on this in this chapter working on these problems, and throughout the rest of the semester. These are beautiful methods. I like them because, for lots of reasons. Another reason I like them is that they can be automated. These two methods, mesh current and node voltage. These two guys, mesh current and node voltage, are mechanical, and that means you can write a program to do them. And that is in fact what's done. Is that these things are done by software using similar methodologies that are mechanical. That's not why we're here, though. We're here to learn circuit concepts. We're not here to write programs. We're here to learn concepts and internalize those concepts so that we have an intuitive understanding for how circuits work. That's why we're working everything by hand here. Okay, that's important. All right, the next thing in this here chapter, the next important concept now is Thevenin equivalence. Now we're going to go through this lots of times, but right now, here it is, just throwing it all out there. Okay, turns out, which you saw in chapter 1, turns out, or was it chapter 2? I think it was chapter 2, that most circuits can be modeled with this simple circuit here, consisting of a voltage source and a resistor. So we call the voltage source V sub Thevenin, or TH for Thevenin, and R sub Thevenin. Most circuits can be modeled with this, and that's what we were doing in chapter 2 when we had tables of voltage and current measurements. Those voltage and current measurements could be taken at any two terminals for a huge circuit. That circuit could be as simple as this. It could be an actual voltage source and an actual resistor, or it could be a huge thing like a city. It could be an entire city, or it could be a power plant, or it could be a big section of a microchip. But at those two terminals, if you measured V and I, you could model that entire circuit with this simple device. So it's a modeling device. We use it to simplify big giant things and simplify them into just these two little guys so that we can do some calculations, right? Very, very powerful. Okay, so what we want to be able to do is find the Thevenin equivalent. So given a circuit of any type up to, super complicated circuit, we want to be able to find the Thevenin equivalent. So there's two steps. There's step A and there's step B. These are two separate problems. Don't mix them up. These are separate problems. But the first one is find V Thevenin. Okay, V Thevenin is the open circuit voltage. It's the voltage across here when there's no load. Okay, all I'm going to say here is that there are various methods, because to go into any one of these methods would just take too long. Typically we're going to use node voltage method, but there are other methods. Okay, so first you find V Thevenin, and then you're done. That with part A, that's one problem that you do. Then you kind of start over and you find R Thevenin. Okay, now for R Thevenin, we have three methods to find the Thevenin resistance. Method 1, method 2, method 3. Method 1 we call the open circuit method, where what you do is you're going to have current sources and voltage sources. That's why I have these little circles. You open the I's and you short the V's. So I remember that by eyeballs, like open your eyes so you can see. Open the I's and short the V's. And then you use resistor simplification. So I'll have to show you a problem on that, and I don't want to do that right now in this introductory kind of thing because it gets too much. But that's the first method. And we'll look at some examples later. Okay, the second method is called the test source method. What you do there is you take a source, you take a voltage source called V sub test. And now think about this abstractly. If you did that and you had a voltage that you could adjust on here, then when you applied a voltage to this circuit you're testing, you'd get a current flow dependent on this voltage. And this thing would appear to be a resistor because the voltage, this test circuit that you're testing would appear to be resistant because by Ohm's law, the ratio of these, right, VT over IT, is going to give you R Thevenin, right? This guy won't know that this isn't a resistor. It'll behave as if it were a resistor. That's one way to think about it, and there's some more ways to think about it that I'll show you. But for now, I just want to kind of give you a high level reference. Basically, you can look back on this sheet on what to do and the which method to apply at a high level. But you're still going to do this open I and short V thing. So I've shown that by just crossing out the circles, because that means you're making the I's into an open circuit and you're making the V's into a short circuit. That is, you're turning the V's into a wire, right? You're just replacing the V's with a wire for both of these methods. And for the current sources, you're just removing them. You're making them open circuits. Okay, then if you have any diamonds, you leave them. So this method works with diamonds. And this one up here won't work with diamonds. That is, dependent sources are diamonds. So you leave the diamonds, you put in this VT over IT. Okay, then you do various methods that we need to talk about later to solve for this right here. So you don't need to solve for VT specifically or IT specifically. You just solve for the ratio of those two because that's R Thevenin. All right, this is introductory. We'll go into more details later. The third method we have is the short circuit method. What you do is you short out the terminals, and then there's going to be this current I sub short circuit associated with it. And at that point, the only voltage in the circuit, if it were in fact a Thevenin circuit, right? Sorry, I'm off the screen. But if you shorted this out, right? If you shorted this out by Ohm's law, by KVL, right? If you shorted this out, then by KVL, the voltages across here must balance. That is, the voltage at this source must balance the voltage being dropped here if you shorted this. So by shorting this, by shorting a more complicated circuit down in here, you've found R Thevenin if you know I sub short circuit and V Thevenin. Okay, so if you've previously solved for V Thevenin, then you do this and you solve for I sub short circuit, then you can solve for R Thevenin. Okay, so in this third method, you're actually going to solve for a value for I sub short circuit, and then you'll use the V Thevenin that you solve for in step A. But in this method here, you're just going to use you're going to solve for the ratio of these two. Yeah, this is an introduction. That's why we're going to spend twice as long on this chapter as we do in the others, because we need to go through these in more detail and work lots of problems before they really sink in. All right, next concept here is something called source transformations. So it is possible. Well, the idea is that if you have a voltage source in series with a resistor, which is what we saw with R Thevenin, or the Thevenin equivalent, this thing here, Thevenin equivalent is a voltage source in series with a resistor. So more generally speaking, if you have a voltage source in series with a resistor, then you can turn that into a current source in parallel with a resistor. So you can turn the Thevenin equivalent into something called the Norton equivalent. But you can also just do this with any circuit that has a voltage source in series with a resistor. You can just transform it into this other thing. a current source in parallel with a resistor. And the way you do it, there's two steps. You just move the resistor, just flat out move it. And then you solve for the unknown using Ohm's law. So for example, if I had this, say I had a voltage source in series with a resistor, and I had a 20 volt source in series with a 5 volt resistor, then I can just move the resistor down here. I just move it to a parallel arrangement with a current source. And then the resistor just the same value, 5 ohms, but the current source is you solve using Ohm's law. So you just I equals V over R, 20 and 5, you get 4. Put it in there. Okay, this is a really nice technique for circuit simplification. You can do these transforms, and once after you've done these two transforms, you can do series and parallel simplifications that we saw in chapter 3. It's pretty cool. Okay, last concept is max power transfer. Okay, this is really nice. I really like this stuff. You'll see why. But let's say you have a Thevenin equivalent, right? You have imagine this is an open circuit here, and that's a Thevenin equivalent. You have V sub Thevenin and R sub Thevenin. So this could be something gigantical, but you've modeled it with this simple little circuit. Now, what you want to do is hook up things to that. So say you hook up a load to that, like the V Thevenin and R Thevenin could be a power plant, and then our load could be the city that you're driving with the power plant. Okay, or something like that. Smaller things than that as well. But okay, you've got this source and then the resistance of the source basically, and then you've got this load that you're running. So I've got an arrow here showing me this is a variable resistor. So that simulates a load that's changing, very much like a city. Right? A city, people wake up in the morning and turn on the stove, make some coffee, wash their face and stuff. So they use energy in the morning, and then it grows throughout the day as it gets hot and whatnot, and then they go to bed and the power goes down. So it's like this load resistor being adjusted for various loads. So as you do that, well, the derivation is skipped here, but as you do that, you could plot the power that's being sent to this resistor. So there's power leaving this resistor. There's also power leaving this Thevenin resistor. There's heat leaving this guy, and there's heat leaving this guy. But if you graph that heat, right, if you graph the power leaving the load resistor versus the load resistor, you get a shape that looks like this. That's very interesting. So what we're saying is that as the resistance of the load increases, you get this shape. So when the resistance of the load is 0, the power is 0, because it's like a wire. There's no heat being lost in it. And then at infinity, when the load resistor is at infinity, it's like an open circuit. This behaves like an open circuit, and then there's no current flow, so there's no power. But in between that, it has this shape, and it rises, and then it peaks, and then it starts to fall like that, asymptotically down to 0. And it reaches this peak at this condition. Okay, so the maximum power that leaves this resistor happens when this load resistor is the same as the source resistor. Okay, and that's interesting when you think about it, because it means that when you're sending maximum power to the city, let's say this model's a city, when you're sending maximum power to the city, the same amount of power is leaving this, because the resistors are the same. So therefore, they're going to be dropping the same amount of power. So half the power is wasted, right? In the middle of the summertime, when everybody's running their air conditioner and the maximum power is being sent out, half of it's wasted in the transmission lines. Okay, that's not exactly true, because that would be true if they were running the system at maximum power. That doesn't necessarily mean that that's what they're doing. It's a little more complicated than that, but we'll talk about that. Okay, that was a review of all of these concepts. You know, you can refer to these handouts as needed to help kind of give you an overview of what we're doing in there. But we're going to spend a good 2 weeks just working lots and lots of problems. Okay, hope this was helpful to you. See you next time. Bye-bye.